Hi everyone, welcome back to my channel, and today we are doing Diophantine equations. We'll be doing a simple problem and just going over how to solve them. Nothing too intense. I'd say these are pretty straightforward to solve. You just have to, internalize the theorem that I'm about to show you, which is this theorem. So this is our theorem, and it pretty much tells us how to solve these types of equations. So what we have is, if x is equal to this x naught and y is equal to this y naught, and these are integer solutions to this equation, ax plus by equals c, then for every integer t, these things right here, this x equals x naught plus bt over the GCD of a and b, so the GCD of this of a and b, and y is equal to y naught minus at over GCD ab. These two will be also solutions that satisfy the same equation, ax plus by equals c, and this is the Diophantine equation that we're solving. So now let's do an example, and you'll see it's pretty straightforward. So this is our example. Find all integer solutions of 54x plus 38y equals 8. So to start looking at this thing, we need a few things. We need to have this, we need to have x naught, and we need to have y naught, but that seems a little vague to find right now. So we also see that we need this GCD of a and b, and that is something that we can do with the given information. So let's solve for the GCD. Solving GCD of a and b, and so our A is 54, this is our A, and our B is 38. Wait, I meant to write B. So GCD of 54, 38. That's what we're doing. And to solve the GCD, we use the Euclidean algorithm. And Euclidean algorithm is pretty simple. First, you start off with the number on the right, and we have 54. And realizing my sorry about that. So we need to find the GCD of A and B. So A is 54, and B is this 38. So now we have to solve for GCD of 54, and 38. And to do that, we use Euclidean algorithm, and let's just go through that. It's pretty straightforward. So first off, you start off with your bigger number, 54, and you write it in terms of 38. So we have 54 equals 38 times 1 plus 16, and that's in terms of 38, and we have this remainder of 16. And we also want to rewrite this, just flip it around, and we write 16 equals 54 minus 38 times 1. So it can also be written as that. So you want to make sure you also write this part, because this will come in handy later in the problem. So next off, we want to write 38. Let me just use a different color. We want to write this number, 38, in terms of 16. So we have 38 equals 16 times 2 plus 6, which is the remainder. And that is how you write 38 in terms of 16. And we can flip it around. We see that 6 is equal to 38 minus 16 times 2. Now, same thing, we take this number, write it in terms of this number. We have 16 is equal to 6 times 2 plus 4, which is the remainder. We flip it around, we see 4 is equal to 16 minus 6 times 2. Again, write this number in terms of this number. And we get 6 equals 4 times 1 plus 2. Flip it, 2 equals 6 minus 4. And again, write 4 in terms of 2. This is just Euclidean algorithm. And you'll keep doing this type of thing until we get to somewhere like this, where you have 4 equals 2 times 2, or a number is equal to something without a remainder. So as you can see, this 4 doesn't have a remainder when written in terms of 2 because there's only 2 2's in 4. And that is where you can end your Euclidean algorithm, and that's how you know your GCD is 2. It's this number right here. That's your GCD. So we have found our GCD, which is this. Now we can move on to the next step, which is actually trying to solve for x naught and y naught. And to do that, we need to use linear combinations. So now let's move on to the next part. Well, here I'm just showing that 2 divides 8, which means this is true and our equation has an integral solution. So now let's move on to solving for x naught and y naught. So we have to write 2 as a linear combination of 54 and 38. So we want to write this GCD2 as a linear combination of A and B to kind of mimic the Diophantine equation. So to do that, we start off with 2. Yes. Sorry, I need 2. So we start off with 2. And we know that 2 from above, from our Euclidean algorithm, that 2 is equal to 6 minus 4. So we can start off with that. 2 equals 6 minus 4. Now we want to kind of play around with what we have and try to achieve this part using only 54, using 54 and 38 multiples of, 54 in terms of 54 and 38. So you'll kind of see what I mean as we move forward. So we can rewrite 6 and we can rewrite 4 because we have 4 equals 16 minus 6 times 2 and we have 6 equals 38 minus 16 times 2. So exactly, we replace, well here I replace the 4 with the 16 minus 6 times 2, and I will replace the 6 with the 38 minus 16 times 2 minus 16 minus 6 times 2. And again, these right here are just parts of the Euclidean algorithm that we flipped over. That's why I said it's important to write this part. This stuff was important to write in our Euclidean algorithm computations. So now we have 38, so we don't need to do anything with that because we want everything in terms of 38. But we have the 16, and we have a 16 here, and we have a 6 here. So we can replace those using what we have up here, because we have something to replace 16, and we have something to replace 6. So on to the next step. Here we have replaced this, we replaced the 16 here, this 16 here, and this 16. And it is simplified into this. Oops. Sorry about that. So we need to replace this 16 and we need to replace the 6. But before we do that, we can actually make this a little easier for ourselves. We see that we have 38 minus 16 times 2 minus 16. So if we were to distribute this negative, this would also be 38 minus 16 times 2 minus 16 plus 6 times 2. So this means we can combine these two terms and make it into one term, which will make things simpler. And we can also replace this 6 with this 38 minus 16 times 2. So doing that, we have, like I said, we have 38 minus 316 by combining this 2 times 16 minus 16 will give us this minus 316, plus replacing the 6 with 38 minus 16 times 2. And that is our new polynomial. And that is what we get. So now moving forward, we can continue simplifying, and we do something similar. We combine all the 16s. We have 38 here. We have a negative 316. This is a negative 216, so that will be, this is actually a negative 416, since this is equal to 38. So we're doing something similar. We have, just want to simplify this stuff, 38 minus 316, and then we can distribute this 2. We have plus 2 times 38 minus 416, and combining this stuff, we get, we have 338 because we have 38 here, and we have 2 times 38, that will give us 3 times 38. We have a negative 3 times 16, and a negative 4 times 16, which will give us a negative 7 times 16. And now we can replace the 16 with what we have up here, which was 54 minus 38, and that will give us, I kind of shown too much, but that's okay. We have 3 times 38 minus 7 with the new replacement, which is 54 minus 38. Now we distribute everything, 3 times 38 minus 7 times 54 plus 7 times 38. Now we are finally in terms of only 54 and 38. So we can rewrite this as 2 equals 10 times 38 minus 7 times 54, because we added this 3 and the 7 to get the 10. We just have this 7 right here. So this is our linear combination of making a linear combination of 2 in terms of 38 and 54. So now, looking back at our original equation, we see that we actually want a linear combination that ends up with an 8. So right now we have a linear combination of 54 and 38 that makes up 2. We want this to be an 8. So how do we make that an 8? We just have to multiply everything by 4. So we multiply everything by 4, and we get this 2 becomes an 8, this 10 becomes a 40, and this 7 becomes a 28. And that will give us finally our x0 and y0 values. That will give us the solution to this linear combination, which is y0 equals 40 and x0 equals negative 28. So now we have this y0, we have x0, and we also have GCD 54, 38, which is 2. We have everything to, as you recall, to make these things. We can make these now. And doing that, let's just do that. So we have x equals, what's our x0? Our x0 is negative 28. Plus, what is our b? Our b, this is, remember, GCD of a and b. Our b is 38, so we have 38 times t over the GCD of AB, which is 2. And we also have y equals y naught, which is 40, minus a, which is 54, t over 2. And this is our solution. Our final solution, our final integer solutions, all the integer solutions to the Diophantine equation that was given above. So thank you guys for watching. I will probably put another or a few more examples of something similar or within the same topic. Just let me know what you want to hear. If you have any questions, leave a comment and a like, and if subscribe if you want to. But otherwise, I'll see you next time. Thank you. Goodbye.